We'll start big idea 5 talking about thermodynamics. So when we look at thermodynamics, we're talking about heat energy and all of its interconversions and how that relates to breaking and forming bonds and getting energy out of reactions. In the most generic sense, when we first look at temperatures, we've seen this a couple of times now. A temperature or kinetic energy is a distribution curve. The number of molecules in a sample, some move really fast up here, and some move really slow. They have a little bit of kinetic energy. When we talk about the temperature of molecules, remember the temperature is just an average. Okay, it's around the peak. There's an average kinetic energy in the sample. Some move faster, some move slower. That has implications in gases and kinetics, but in general, this is what temperature is. When we're talking about the first law of thermodynamics, which is one that you probably know verbatim out of a textbook, matter or energy cannot be created or destroyed, only transformed into one kind or the other. So energy is conserved. It's just the general idea. Energy is conserved. This does not work with entropy, but it does work with heat energy. And this is where we get our system and surrounding comparisons. So if energy is leaving atoms or molecules, they're going to the surroundings in the exact same magnitude. The standard here, we'll use that in a little bit here. We often say standard conditions, which is different than when we had gases. Gases, we say standard temperature and pressure. Standard conditions they have this little degree symbol. Remember, that's going to be 25 degrees Celsius. Room temperature is standard, not 0. That's STP for gases, but standard conditions is 25 degrees Celsius. And then we always deal with 1 molar solutions as well when we have aqueous things. When we get into delta H, which is enthalpy, it's the heat energy, standardized heat energy per mole or per gram. We've talked a little bit about exothermic and endothermic, but now we're going to delve into that a lot more. So we want to remember that when we separate things, and this one's a little bit intuitive, that enthalpy is going to be positive. It is endothermic, to break things apart. Anything you're breaking apart, if it's a stick or atoms or molecules, or if it's a bond or intermolecular forces, whatever you have, if you're separating those things, you have to pull them apart. You have to overcome an attraction. There is something holding these together that you need to break. There are forces in here. And if you don't overcome those forces, you're not going to separate it. So you always put energy in to break things apart. That one's pretty intuitive. The other one, though, is when we bring things together, if we form a bond, or intermolecular forces, or whatever, that will give off energy. Much like if you clap your hands, sound energy can come out, sound. If two cars crash together, you would get noise, light can come out of certain reactions. Energy comes out when things form. It's kind of like the excited and ground state. It takes energy to go up, but then when energy comes down in an atom, it returns to the ground state and energy comes out in terms of light. So endo and exothermic. Exothermic is going to be our favorable term. Anytime a system can release energy and be in a lower energy condition, it'll be more stable. It's just the way the universe works. But there are other factors involved as well. So just kind of an overview there, we're going to be talking about enthalpies. To define enthalpy a little bit, or at least to define the enthalpy of molecules, we talk about heats of formation under standard conditions. And a heat of formation is going to be 1 mole of product. How much energy is in exactly 1 molecule, or 1 mole, from its elements in standard state. Standard state means phases as well as monoatomic and diatomic. Because their standard state, we kind of look at those as they have free energy. So anything in their standard state has a heat of formation of 0 kilojoules. So if we're looking at, if we have all of our reactants as elements in their standard state, the only thing we can focus on is the molecule itself, the one product, and that tells us the enthalpy to make that molecule. And it's a state function, so it doesn't matter how we make that molecule, that's just the energy of that molecule. So if we had an example here, hydrogen gas plus 1/2 oxygen gas, diatomic for both of those, makes H2O gas. Now the reason we have a fraction there, this is the only type of balanced equation where we have this fraction, is because the heat of formation dictates that we have 1 mole of product. So I don't want to balance this equation in the normal way, we're just going to get 1 mole. This type of reaction allows us to say, okay, standard state hydrogen has no energy, it's readily available. Standard state oxygen has no energy. Any energy that's measured for this reaction is due solely to the water. So that gives me an absolute value of heat energy for that water molecule. And then we apply that when we get different types of reactions. So those are the heats of formation for individual molecules. We use that when we start talking about heats of reaction. Okay, the heat of reaction. And this is in kilojoules per mole. And there's lots of different ways we can use those heats of formation or various things to do to get the heat of a total reaction instead of one molecule. So let's just outline a couple here. The first one I think is the easiest, but it's really easy to make math mistakes, is the summation of the heats of formation. So we have the sum, and if you just remember products minus reactants, the heats of formation of the products minus the sum of the heats of formation of the reactants. Another one we can use is another summation, but we say broken minus formed. The bonds that are broken minus the sum of the bonds formed. And if you put it into this equation that way, all bond energies are positive anyway. That minus sign takes care of the ones. The reason we put these second is because they're exothermic. So that minus sign kind of takes care of the exothermic. These go first because they're positive, because energy has to go in to break them. They're endothermic. So that's the way that this equation is constructed, based on bond energies. The third one, we can get heats of reaction using Hess's law. And Hess's law lets us combine equations. Doing a little bit of algebra, we can reverse them. We can change the sign. If we double equation, we get double the energy. If we reverse it, we get, if it goes endothermic to exothermic, we can switch those around as well. And then the last one we can use, we'll spend a little bit more time on here. It's going to be just generically thinking about heat. So the units, you remember units often tell you equations. You don't have to memorize a lot of equations. If you know that enthalpy is kilojoules per mole, well, if you have the heat of the reaction, and you know how many moles of the substance you're talking about, I have news for you. That is the equation, kilojoules over moles. So you can just use that. Now we get that, we can get the heat from the reaction. The other big part of this is calorimetry. Calorimetry is going to allow us to find Q for a reaction. Our generic equation, the MCAT equation, just tells us how much energy a substance can hold with a certain specific heat, a certain mass and temperature, and how much energy it needs to change the temperature, and so forth and so forth. But specifically for calorimetry, when we have a sample of water, we measure all of the water data, and then that is the energy of the reaction, because the reaction is the system and the water is the surroundings. So we can take that reaction value over here and just use it, kind of flip that system and surroundings around, go from one to the other. You do need to watch out for that minus sign. That it is the opposite. Whatever your water value is, the reaction is the opposite. But then you can use that to calculate the enthalpy for a reaction. So calorimetry is very useful doing those heat equations as well. And then this is useful another way. Once you have an enthalpy, we can use it to do some stoichiometry with balanced equations. So it's really important to be able to do stoichiometry with delta H's. We briefly mentioned it in the reactions big idea, but we need to use delta H as well. And you can do limiting reactant questions, you can do whatever you want. So if we had a balanced equation, let's say it was 2 sodiums plus 2 H2O makes 2 NaOH. Scroll over here, plus H2, and then we said delta H for this reaction, I'm running out of room a little bit, is negative 540 kilojoules. Okay, negative 540 kilojoules. That is a conversion, because that's kilojoules per whatever we're talking about in our equation. So then you get a problem that says, okay, let's imagine that we had 2.3 grams of sodium. We know the molar mass of sodium. How much energy can we get out? Well, the molar mass of sodium, we've got 23 grams of sodium is a mole. And then our balanced equation is showing us that there are 2 moles of sodium in this reaction. So this is not 540 kilojoules per mole. When we're talking about sodium, it's 540 kilojoules per 2 moles. So we need to get that accounted for there. That comes down here, and we have 2 moles of Na for every negative 540 kilojoules. That is our conversion. And we can relate that to anything we want, but that gives us a way to calculate this out by using our balanced equation and our enthalpy value as a conversion in balanced equations. And that comes out, we get, okay, negative 27 kilojoules. So make sure you know how to use those. If you know the units, kilojoules per mole, we can calculate those a myriad of ways and then use it for some stoichiometry as well. You'll use a little bit of stoichiometry applying those. Let's look at one other thing here. In heating curves, we want to be able to make some sense out of these when we look at a heating curve. So our heating curve here has temperatures and just a generic time axis on the bottom. but we want to be able to read these. How does a substance change from solid to liquid to gas, and what are the energy requirements in there? And we say here I've got the heat of fusion, that's our solid liquid boundary when they're in equilibrium with one another, and that temperature right there is going to be my melting point, where it changes from solid to liquid, or freezing point if we're going down. My other temperature here, if I kind of go across, that's going to be my boiling point, going from a liquid to gas, and then that boundary is going to be my enthalpy of vaporization. So there's enthalpies in there. At our solid, liquid, and gas stages, we want to be able to do MCATs. So if we have a solid, a liquid, or a gas, everything has its own specific heat. We have our MC delta T equation to see how much energy is released at each part. But my delta H's, we do some stoichiometry, because those values are in kilojoules per mole. So we need to know how many moles we have to get all of the heat terms to go from one temperature to the other along that curve and see how much energy we can get out. And it's important to remember here signs as well. If you know the general idea, you don't have to keep track of every little positive and negative. If the temperature is going up, we're breaking things apart, that is going to be endothermic. If we are cooling things down and bringing them closer together, energy is going to be released. Those will all be negative exothermic values. So it depends on the direction. Are you trying to make a solid turn into a gas, or are you trying to make a gas turn into a solid? Don't forget the magnitude of those numbers. The next part of thermodynamics that we're going to deal with will be entropy. That is our delta S term. So the second law of thermodynamics, the entropy of the universe is always increasing. It is not conserved. It is always getting bigger. So positive entropy is going to be a good natural thing. If we have more order, there's a lot of ways people talk about entropy. Order or disorder. I think order makes more sense. If we have more order, more structure, we are losing entropy. Disorder, let's say less order. More chaos, more disorder, which is what entropy really is. We have positive entropies. The positive entropies are favorable. If you have dust particles, your room just kind of gets dusty. It doesn't get clean by itself. When your laundry is in the washing machine, it doesn't fold itself. It spreads out. It gets disordered and chaos. Disorder is just a natural, universal phenomenon. We can calculate that with a very familiar equation. Delta S of a reaction is going to be the summation of the standard entropy of the products minus the reactants. And it's important to remember here the third law of thermodynamics, which is going to apply to that equation, even though it doesn't really make sense the way it's written. A perfect crystal at absolute zero has 0 joules of entropy. The only substance with no entropy is a substance that is at absolute zero, and it is a perfect crystal with no blemish, perfectly structured. Really what that means for us is that compared to delta H, when we have elements in their standard state for entropy, they are not equal to 0. Every substance that we're going to deal with has an entropy. So don't be fooled into thinking that diatomic gaseous oxygen has an entropy value of 0. It does not. And really, we're going to use that to talk about entropy is one piece of the puzzle, enthalpy is the other. Really, we're going to use both of those to talk about Gibbs free energy. Delta G, because this is the one that's going to tell us whether or not a reactions actually happen. And delta G, sometimes we call this work. Can a reaction work? But in physics, it's actual kilojoules. Are we going to get energy out? When delta G values are negative, we use the word spontaneous, or we're kind of going away from that. We're going to say favorable. And if delta G is positive, it is not spontaneous. It will not happen, not favorable. And remember, when we say spontaneous, we do not mean fast. That's kinetics. This has nothing to do at all with speed. Speed is thermodynamic, or speed is kinetics. This is thermodynamics. This just tells me yes or no if. So there's a bunch of things we're going to do to calculate delta G's. So let's just make a list. Number 1, we have our summation equation. Delta G of the reaction, if we know delta G of all of the standard molecules, is the summation of the delta G of formations of the products minus reactants. And these do have standard states of 0, so any element in their standard state is 0. Oxygen, diatomic gas will have a delta G value of 0. Another one, very similar to delta H, we can use Hess's law. Now we don't call it Hess's law because he didn't do this work, but it's the same stuff. You reverse an equation, you can add them together, change the sign, multiply the energies, all of those. The third one, and this is the most important one that we're going to be working with here, is our delta G equation. Delta G, this puts all of our terms together, thermodynamics equals delta H minus T delta S. And we need to be careful here. Delta G and delta H, we often record things where they register. They register on the kilojoule scale. Delta S is often on the joules scale. So you need to make sure you have unit consistency here. When we look at these terms, we want to see under which conditions are reactions favorable and not favorable. So if we look at all the conditions here, let's go with the most favorable ones. You can kind of see mathematically how this works. If delta H is negative, which is favorable, and delta S is positive, which is favorable, then my delta G will always be negative, because our equation is delta H minus, that minus sign, minus a positive is going to give me a negative. So a negative minus a positive, delta G will always be negative. Mathematically, we can think of that way. Thermodynamically, we say both of these are favorable, this will be favorable too. And this was always going to work that way. The opposite of that, if delta H is not favorable, positive, and delta S is more structured, also negative, then delta G, this reaction will never happen. Delta G will always be positive. And then we keep going with that thought, and now we've got some temperature dependencies here. So if my delta H value is negative, well, that's favorable. and my delta S value is also negative, that is not favorable. They're competing against one another. The term that determines whether or not this will happen is going to be the temperature. So we look at the temperature dependency, and we say that this one is good. Let me do this in another color here. That one's good, and this one is not good. Well, at low temperatures, it'll eliminate this delta S term. And at high temperatures, this delta S term is going to take over. So that means this is going to be more important at high temperatures, and it will not happen. So we get a lot of these in phase changes, and we see the temperature dependence here. At a low temperature, the reaction will work because delta H is more important, but as that temperature term gets higher, the entropy starts to be more important. It will not work. Delta G will be positive. So phase changes, all phase changes are going to fit into one of these two categories here because they have thresholds where at a certain temperature above that it will work and below that it won't. So delta H for this one is now not favorable and delta S is favorable. So now the temperature is going to do the opposite thing. At high temperatures, my delta S is going to be more important. So I want my favorable term there. High temperatures, it will work better. So at a low temperature, it will not work because delta H is going to be more important. But at a high temperature, it will be favorable. Delta G will be favorable. So really analyzing that equation can get very, very, very important. It's really important to know here, especially when we're looking at phase changes. All right, let's see where I can squeeze this in here. Whenever we have a phase change, delta G is 0 at the temperature change. Okay? There's a boundary where delta G will go from positive to negative. So at that boundary, the point when it goes from a negative number to a positive number, there's a temperature threshold where delta G equals 0. That is where phase changes occur. Okay, so phase changes occur at that boundary. So often, they never give you that in a problem. They'll just say, you have water turning from a liquid to a gas. What temperature does it do that? Well, delta G equals 0, and now you can plug that into this equation and see how the rest of it's going to work out. There are a couple other related equations where we can use delta G and branch off into some other categories as well. So let's see what else we can do with delta G. If we had delta G, we could calculate cell potentials. Delta G is related to the cell potentials. Negative N moles of electrons, Faraday's constant, times the cell potential. If we had delta G, we can also calculate equilibrium constants. So all of these are related to one another, RT ln of K. And that's because for a spontaneous reaction, if we think about how all of these work, delta G will be negative. Well, cell potentials, if they're working, if the reaction happens, they'll be positive. And we can get K values, if they're working, they should be greater than 1. So all three of these terms are related. If we have a delta G that's positive, it does not work. Well, we wouldn't expect the cell potential to work either. That would give me a negative voltage. And if it's not working, it's favoring the reactants, so it's going to be less than 1. So all of those terms are related to one another, and we can use that delta G as a springboard to other concepts in chemistry. But that's kind of our overview of calorimetry, delta H, delta S, and then tying them all together into delta G. And that wraps up Big Idea 5.